Welcome back to the lab. If you've been keeping along with this electronic load series, this little project we've been doing, you'll know that we've been messing around with this so-called analysis. We've been developing hardware and running simulations. But is that really even work though? Come on, do I really think that you're all going to believe that we just had to develop a UI before running our tests? Heck no! Let's burn some watts. Let's pump some joules through this system and see what gives first. Let's see what gives first. Man, these opener bits are fun. Okay, transitions. Yes, it's time to test the electronic load. All right. Our testing went through a few phases, and we did a little live stream when we were doing it. So let's walk through the first phase, and that was fixing the discrete BJT buffer. The gate drive buffer didn't work quite how we had hoped on the first go, and that's okay. Technically, the design works, but it just doesn't work well enough to be worth the cost in components. Because, here's what I think happened. Well, the primary stage isn't perfect, which tends to leading a little steady state current, just trickles right through the second cascade of the buffer. Oh wait, that means we're dropping somewhere between 15 and 30 volts in one of these tiny 3904 or 3906 transistors, and then eventually one of those tiny dies turns into silicon soup and fails as a short circuit. It's basically a combination of the fact that the transistors aren't perfectly matched and the fact that we're trying to have a low ohm output resistor, in this case 2 ohms. So any leakage current turns into pretty extreme power dissipation in those little parts. So there's an easy solution to this, and it seems like it's always the solution to problems like this. You just increase the resistance. So we tried 2 ohms, 5 ohms, 10 ohms, 100 ohms, and turns out the resistance where this buffer stops going nuclear is somewhere between 500 and 1,000 ohms. And that's kind of the problem, because see, the resistance where the output of our standard op amp is able to drive the gate of our FET is 500 to 1,000 ohms. So, we've basically just gained nothing, because the op amp would drive it at exactly the same speed because it's got an internal buffer stage, and then you put the resistance, so it's like we're not even getting anything for adding all those parts. Of course, we could add bigger BJTs. We could try to optimize that buffer to use matched pairs. There's a lot that we could do. We could try to use a bigger, higher current op amp, or like a small audio amplifier chip where they make those. We could try to use something like that, but the performance of this system is way better than I thought it would be with a 1 kilo ohm gate drive resistor. I thought this was going to be all over the place, but it was really good. It was really good. So I guess that leads us right into transient response. The issue with keeping this 1 kilo ohm resistor is exactly this. We just made an RC time constant and introduced phase delay into that PID compensator or MOSFET control loop that needs to deal with. Our PID compensator needs to handle the fact that when it outputs a voltage, it's not immediately present at the MOSFET. I don't know that that's a problem, but it's just something that we need to think about. It's not the way the system was designed originally. We've just changed the system. So hopefully we didn't change it too much. Hopefully it still works well. We did a few load steps, measuring sub 0.1 amps per microsecond, which isn't great for an electronic load, but it is probably good enough. The rate of rise was measured when we were doing that from 10 to 90% of the waveform of the output value, so I can probably tune that to be a little more aggressive at the cost of some overshoot. I don't know. I think I'd rather just keep the system below the set point and avoid ringing, avoid higher frequency content in the load waveform, but we'll see. I'll think about this. I will. Either way, it's good news for the buffer that we don't really need it because it didn't really work. At least good enough news that we have something to continue our testing with. Let's say that, okay? So there's nothing left to really do but test the regulation. I'd love to walk through it all today, but I want to keep this in bite-sized chunks and just release it as it makes sense. So we're just going to focus on current regulation today. We took some data during that live stream. I circled back, collected a little more, generated this table, and whew, is that ever pretty. Our results as follow. Overall, 0.01% line regulation between like 0-ish and 30 volts. And so that is the output current changes very little at the same set point when the input voltage changes a lot. And that's sweet. That's great. The base accuracy isn't fantastic or good or great. And I want to dive a little more into why in a moment. I see two effects. I see a primary error cause being the offsets of the system, that being the tolerances of the voltage reference, the shunt resistor tolerance, the ADC errors, and yeah, that's basically it. But there might be a secondary effect. That primary effect is what we see slowly trending towards zero error as current increases. As the set point increases, that those fixed offsets don't bother us as much, though so some of the percent errors will continue to factor in. Unfortunately, the low current portion of that curve looks pretty terrible. And I think that as we approach lower currents, the 8-bit DAC might be starting to hold us back. I think a combination of the low resolution of that DAC and the small output voltage that we're like putting into the regulator is driving our error to an unhappy place nearing 10%. That, combined with the fact that our other errors are starting to get divided by almost zero, makes the percent error explode because we're dividing by nearly zero. So that's unfortunate. It's just kind of the nature of the beast, though. As it stands, calibration requires non-volatile memory and special software. I'd love to calibrate this, especially at low currents, at low output ranges. I think it will help a lot. I want to try to improve that situation with hardware first and rely on software as a last resort. But before we wrap this up, I want to chat cooling because I just want to be very upfront about this. I let the design soak for a thermally significant amount of time and found that 53 watts is the maximum power that keeps our heatsink temperature at 70 degrees C. Under normal circumstances, I'd push the design a little further, but I know just as well as you that thermal interfaces are rated in degrees C per watt, meaning that we're pushing 53 watts, and that's in the numerator. So I know that even if our thermal interface is good, whatever that is being multiplied by a factor of 53. What that boils down to is that to keep the die temp below 115, and that's not even being very kind, it's about 10 volts or 10 degrees of margin. We need to get through two thermal interfaces with less than 0.85 degrees C per watt of thermal resistance. That's not a lot. Our part's rated for 0.05, and the interface material is rated for 0.14. That's degrees C inches squared per watt. Yeah, that's right. It's degrees C inches squared per watt. We've got about 1.2 square inches for thermal conductivity, leading to a total thermal resistance of 0.172 degrees C per watt for this part. That's actually better than I expected. That's not half bad. That's a very good thermal junction. So I guess we can push 75 watts through the part if we keep the heatsink below 102 C. We can push 100 watts through the part if we can keep the heatsink below 97 C. Or if I dream a little, we can push 500 watts through this part if we can keep the heatsink below 30 degrees C. It's not bad. Even though the SOA curve allows for up to 1,000 watts, practical cooling solutions simply just cannot handle that. We need sub-zero heatsink temperatures with the chiller to get that much power out of this part, but our sad little heatsink, the CR40 from Omite with the sad little 40mm fan, it just, even with the shroud, it's just not enough. We need a better pairing. We need a more appropriate heatsink for this part. And that's a little scary to me because I didn't expect this to be good enough. I expected to need to improve it. But we're talking about trying to achieve a 10x performance increase in cooling between this iteration of the design and the next one, and that is not a small change. That's not tweak territory. That is rip it up and start over territory. That is scary. I was expecting this to be off by a factor of 2, maybe 3, maybe 4, but 10? An order of magnitude improvement required. That just doesn't happen overnight. Yeah. Don't get me wrong. The CR40 did everything it needed to. This is a dev kit. This was meant to be a really rapid dev kit to test some of the control features and get the software development going and things like that. This wasn't meant to be a perfect thermal solution. It's just meant to be reasonably compact and cheap. So that's basically where we're at, and that's why moving forward, we're going to try to use a computer CPU cooler. We're going to use the LGA 115X cooling mechanism, and there's going to be a lot more to come there. It's going to be fun, so make sure you don't miss it. That's all we've got for today, but if you like this video and can't wait for more, let me know by getting subscribed, hitting that like button, and leaving a comment down below. Coming up soon, we will be testing power regulation and resistance regulation for this design, and I cannot wait. If you want to support the channel, check out the links in the description of this video where you can do exactly that. Check out our live stream if you're interested in that sort of thing. Same information, just longer format, different vibe, a little more informal. It's a lot of fun, and you just might enjoy it. Thank you to everyone who's taken this step to support us directly on Patreon. It really helps to keep this all possible, and I appreciate that. Thank you for leaning into EE for Everyone and helping us to do what we love best. Get this content out to help people learn and inspire you to learn by doing. Most of all, I hope that you learned something great today, and I hope to see you again soon. Thank you for watching EE for Everyone. Thanks for staying till the end. Bye.